So during the last lecture, we have already taken a small look at how C and C++ work under the hood, how we can basically interact with a C++ or object just from plain C. So we did some hacking, so to say, and today we will deepen our understanding of such low-level mechanisms and how code can be manipulated to behave differently than what one would normally expect. So we'll create a new project for that. Let's call it function hacking. And we start again with a console project. And what we will be trying to do now is to manipulate the behavior of a function loaded from a DLL. So DLL loading we have also taken a look at during the last lecture. So we are familiar with how this works. As you might remember, I mentioned that there are two ways how DLLs can be loaded. One is an explicit one, as we did, where we use the load library function, and then we can operate with the DLL. And I mentioned back then that there is a second way how DLLs can be loaded, a much more implicit way. There we would use a corresponding lib file, so a library file. But this library file, instead of containing the full code, would only contain short descriptors of what to expect in a DLL, and then the linker will create all the necessary DLL linkages so that we can address functions from those DLLs more or less directly. And in some way, some of the functions you have seen me using were already loaded this way. For example, heapalloc and related Windows functions, virtual free or virtual the one to change virtual protection, to change the page protection, also are functions loaded from Windows DLLs without using DLL load, but instead they are just part of the standard library set, which is which can be configured here. So the system is including some standard libraries. It doesn't show us exactly which ones, but if you want to add your own libraries, you can just add here additional library files and they will be included in your project. So today let's start with a simple function which opens a Windows message box. And yes, those functions can be called without any issues from a command line application as well. Since Windows is foremost a graphical user interface, the command line applications are just like a reduced feature set application, but you can always just decide to use more advanced functions. So we have included Windows H, and let's call some simple functions. So message box, correct capitalization and fear of typos. And you can see there are functions like message box A, and there will be somewhere message box W. And the actual message box as such is just a preprocessor definition which directs us to one of those. And the A ones, A stands for ASCII, are the normal simple ones which take just characters, while the W version of Windows APIs always takes the Unicode version, so white strings, and we will of course stick to this. And it takes a few arguments. So first would be a parent window, which here in the console application we don't have, so we just pass null for it. That is not a problem. Then we can specify some text, some white text. Let's say let's call it, let's just call it text for now. Then we can specify a caption, so window title. Let's not be too creative about it. And then we can specify a message box type. This allows us to select which icon will be shown. There are like 4 standard icons, like warning, error, question, and There was one more warning, error, question mark, and information. And then we can also select which buttons are shown. So we can request an OK message box, which just offers you to press OK. We can have one that says yes, no, or yes, no, cancel, and there are a few other variations. But that is not so important. So for now, let's just message box with an OK button and with an information icon, MB icon information. So if we go to those definitions, we can see what we have at our disposal. There are like those are the standard, the basic values, and for the messages, they are the types like OK cancel, retry about ignore, yes no cancel, yes no cancel, retry. If you would want like a fully custom message box, then you would need to actually make your own, but here we just want some Windows function that we can manipulate and see the effects of our manipulations instantly. So as we see, it works as expected. The message box is shown and then the application terminates. We can also step through it to see how it behaves, but before we do this, we will change a few settings. As you remember, there are quite a few settings that make the generated code slightly more complicated than it needs to be. So we can disable this code generation. We don't want any runtime checks, and we don't need this as well. Okay. So let's see. So as you see, the call to a function in a DLL mostly looks like just a normal call. There is nothing particularly special about it. We just see here that there is something called underscore implement message box face. So let's step through it. We won't put out the arguments, and when we go there, we see that we are already jumping inside a user32 DLL, which is part of Windows. We can activate here symbol loading so that we get the function names for this one as well. And we see we are in the message box W. We go back where we came from. This thing basically is so what we are basically doing is we are jumping to a function which address is stored in this variable, and for every such automatically imported function, the linker will generate such a function pointer which will be populated when the image is loaded by the operating system's loader into memory. It will also automatically load all the necessary DLLs. So this process can be automatized quite well. What we want to do now is we want to manipulate the behavior of what this function is doing. So we have already seen how the call works. So for our own purposes, we would want to have the direct address. So let's use a function, the function we already know, or let's use another function. So you can either load library multiple times, and each time you do it there is a reference count incremented, and on the last free library the library is actually unloaded. Or there is a function which allows you to get the address of a library if it is loaded, or null if it's not. So what we would want first is the actual address of the DLL. We could of course also try to just access this variable underscore implement message box, but let's go with a more manual approach. So h module user32 is equals get module handle w, which takes the DLL's name. Yeah. So this will give us the already loaded DLL's address. We here implicitly assume this DLL will be loaded. And then we want to get the address of the message box function. So for this, let's first create a function pointer and a variable to hold our own copy. So type def integer klammer p calling convention asterisk p underscore doesn't type underscore message box w. Oops, now the argument list, which we can basically just copy from the existing header, zack. That's nicer. Okay, so we will create a variable of this type. This we can just select some name, but let's go with this name, and then we can use a get pods address. Since we are here in a C file, a CPP file, we need to cast always the types correctly. Get pods address. User 32. So this is quite exactly as we did it before with our own DLL. Just that here we are loading something from a Windows DLL, and we run it. We can see that this thing is here, just the address in the DLL, and when we then go back and step through everything, we end up exactly where we want in our user32 DLL. For now, we have not yet made any changes, but we will. So what we can do, for example, the simplest approach would be to create some own function which will replace the existing function. So let's create a C function. So we use this extend C keyword to ensure that whatever we define here will be nicely formatted just for normal C usage. This we might not need. Let's make this a bit nicer. And of course we need to change the name, like my message box W, for example. And for now let's just return 0, so let's make the function do nothing. Okay. So our goal will be to change the code inside the library such that whenever the program from wherever calls messagebox W, it will in turn call our my messagebox W. So this is quite easy when we just need to override the beginner of the function with some jump instruction to our own code. So for this we can first create some small helper. Union, zack, let's call it code, type. The idea of this helper is to allow us to write different sizes of data quickly and then advance to the next free address. U64, thank you. Yeah. Okay. So let's initialize this thing. Code pointer bytes will be equal our message box W, which we have here. Of course, we need to cast types again. In C++, types are much more strict. Okay, and basically what we would want to do is we would want to load the address of our own my message box, and then we would want to jump to this address. So we will need a representation of those instructions as bytes. So first thing what we want is move args, comma my message box. And the next thing is jmpl args. But for this we need to write some direct code, and what is very helpful for this is to use some sort of online assembler, so that we can just write simple code, simple assembler code online, and the thing will then just spit out for us. No, I don't like that one. Where's the good one? Yeah, Google shit. Sorry, Microsoft is shit. Let's go to Google. Yeah, this one. And this page, for example, allows you to just write assembly code, and then it will generate you the bytes that you need. So let's go with our code here, of course, without the comments. And here we need to put some address, so let's go with 0x, and then a pattern that we can easily recognize, like FF 6 oops, 1, 2, 2, and 3 missing letter here, assemble, and it gives us basically the byte representation of our two assembly instructions. And we can see that this part here basically is the address which we have written here, while the MOVRAX itself are just the first 2 bytes here. So let's write them down. So we write a word, so these are 2 bytes, PW, and using this helper we can use first of all the asterisk operator to write something to memory, and then we can use this plus operator to advance by the amount of bytes we have written. So this is quite a convenient mechanism. One thing to remember is of course that if we use the 0x notation, the decimal notation, we need to reverse the order of bytes, so it will not be 48 B8, but we need to write B8 48. Oops, that was the wrong button. So B8 48. And this, when it's then written, will end up with the right thing. Then we need to write the address, so we can use the same mechanism, just that and we need of course a semicolon, that we write a keyword. This will be just equals our 64 function address. We can use the name of the function directly here. It's an address, so let's put this here, and then we need our jump instruction. So jump instruction was again just 2 bytes. When we reverse it, it will be E0FF, and it's again a word, so only 2 bytes. E0FF. Let's move that a bit further out. Okay, and we of course need a semicolon. And at this point, this is like the simplest manipulation we can do. Of course, this kind of will not work, as we have learned earlier. It's probably protected memory, so we first need to lift the memory protection. We can do that with the virtual protect function, which just takes the address where we want to write something. So it will be this thing, comma. Then it takes the size, so how much bytes we want to unprotect. Let's make a variable for this. Is equals, for now let's just go with, we only need a handful of bytes, let's go with 16 bytes. Effectively it will still unprotect an entire page, but the size is important, that if we would be on the somewhere on the page boundary, that it then can know that it needs, how many pages it needs to unprotect. Or if we would specify a size larger than a page, then the same would apply. It would then unprotect multiple pages. So we want page execute read write, and of course we want to save the old configuration, whatever it was, and once we are done, we then just restore it like this. So let's run, and now let's step through the function. So we are jumping, and what do we see here? We have our own code that kind of is not shown properly. Let's hope it will. I think we have some mistake somewhere. Let's see. So we write a word. We forget here plus plus. So we didn't advance and just overwritten a part of our address. So that was of course not quite right. Let's repeat it. Zack. Okay, that looks much better. We have our MOVRAX. We have some address, and then we have JumpRax. So when we execute the 2 instructions, we end up in our function, which for now does not do anything. So we could include stdio so that we can print f. So we could, for example, f percent capital S for white characters, and then just print the text to the console. So let's put a breakpoint here. So now, as you see, we of course don't get a message window, but instead the message box's content has been written into the window here, because our function has now another implementation. So such mechanisms can be used basically to change the function of more or less any function that we are loading into our memory space. The way we did it now is kind of limited, because we are, by doing it so simply, we lose the ability to modify the to use the original function. So now we couldn't in any easy way call message box theme. So of course the next thing we will do is try to fix this and improve it such that we will be able to call it. So one very simple approach would be of course to just make a backup of whatever we have overwritten here. So let's make a variable for that, char. Let's call it underscore backup message box w, and let's save, I don't know, a few more bytes for now. Then here we can of course grab the size of our backup so that we are consistent. And to backup this, it's quite simple. Simply before we start modifying it, we just use memcpy, memcopy. Destination is our backup. Source is our this message box, comma, and size we already have here. So we will have the original bytes, and then inside our detour function, as such functions are professionally called, we can just more or less simply undo what we have done before. There are of course a lot of limitations to this mechanism. First of all, while we are overwriting the code here, if we would have multiple threads running, then that might cause some of the threads to crash, because the code would be in an inconsistent state. So here, if you only have one thread running, it's easy to do such things. But if you would have an application which is already doing things, then later modifications are rather risky. So usually, if you want to do such modifications, you would try to either install them very early in the process start before additional threads are created, or the other option would be of course to enumerate all the current threads, suspend all of them except the own one, and then do the modification. Although this in practice is even more complicated, because of course you could suspend a thread while it's in the middle of executing the code you want to modify. So this also would not be sufficient. So there you would then need to detect the situation and then resume that thread and then suspend it again and try to catch it in a moment where it is not actually executing the code that you are going to modify. So the modify at load approach is much safer, and of course this restore mechanism is susceptible to the same problem if we want to restore things. And then if there is a second thread trying to use this code in the time when we are restoring it, then it might also end up in a crash. So usually one would not do it this way. I will show the other better way shortly. So now, since we have restored it, we could actually show the message box. So let's do it. We know its address. We can leave this printf here, and we can just call our message box, and we shall modify one of the text. So let's keep the text fine, but let's change the caption to hacked message box, comma, we keep the same type, suck, and let's run it. we don't want to step through it this time. So we get our hacked message box with the message text unchanged. We could have also changed the icon, of course, if we wanted to, and it still printed the text out here. The downside, of course, now is that if we would have multiple message boxes, so let's create some slightly more elaborate test case. If message box name null message text fail now question mark title is this title and then yes no question information question and this is ID yes. Oops. So if this is yes, then our application will show another message box saying failed icon. That's the stop icon, and return -1. And of course, in the other case, we keep here success icon information return 0. So as said, we could somehow influence what the first box is doing, but would have no influence on the later boxes. One approach, of course, could be potentially to also back up our detour code, and then after we have called message box, then again restore our hack and then just bounce back and forth all the time. But as said, this would fail terribly in a multi-threaded scenario. So we can of course see this behaves. So we have here still our hacked message box, but the next one is already unhacked, and it also doesn't show doesn't print the text anymore. So our goal here would be to find a way to safely and reliably call the original function without having to overwrite our nice detour code, which invokes our own handler. So let's comment this out. This also can go. And a simple approach, or at least a somewhat simple approach to achieve this goal would be to just copy the code of our of the original message box, the code which we overwrite somewhere else, and then once that code has been executed, add a jump instruction so that it will jump to our own to the original code, basically bypassing our detour code. So we want some sort of technical term is a trampoline function, which will do whatever is overwritten and then jump back to and continue the original function's execution flow. In practice, there might be situations where this does not work ideal or not at all. For example, if we would have a actual function which would for some reason jump back to the very begin of itself, but practically you won't see such functions in the wild. Usually the functions will have some sort of simple prologue code at the beginning, and as we have seen here, our basic detour code is not really long, so we have 2 characters here, 8 characters here, and 2 here, so in total only 12 characters. Depending on how we are doing things, we could complicate things more and in turn here reduce this to only 4 characters. But this would require our target address to jump to be located within plus minus 2 gigabyte in the memory space of our target DLL, which is doable, but as I said, it just adds some additional complexity. So the first thing we should do is we should disable everything and then just see how the unmodified actually we don't need to disable anything, we can just put a breakpoint here and then see how the unmodified code looks. So this is how the standard Windows message box code starts out, and this also changes from version to version of Windows, so it's not something that you can rely on staying the same. So in a practical everyday application, you would need to automatize what we are going to do here manually as well in some way. There are libraries available that do it, like Minihooks, or also the DTOS libraries offered by Microsoft on GitHub. So it does what we will be doing here by hand, basically automated on its own. So let's copy the whole function. It's not very long, so let's just grab everything and write it down here, so that we have it. Okay. And what we'll be doing is basically we'll allocate some new memory. Like this. We'll allocate some new memory, and then we will put our trampoline code into that executable memory. So what we also need will be some new function pointer for this. So we'll just go here and call this trampoline message box there. This will be our own function, and then here we will use it to show the hacked message text. And what is very reasonable here is to really allocate memory as close to the original DLL as possible, so that we can easily modify the existing code and don't need to change short jumps into long jumps and so on. So we can use virtual alloc, which is a Windows function, to allocate memory at a suggested address. So let's do that. For you char, and we of course want to suggest you char our system, the original function. But of course the thing is that this might not necessarily work out. So we don't have a termination condition here. That will be later, although we could actually even put one here. Basically, if this thing, because we initialize it to 0, so if this thing is not 0, so while this is null, we continue doing things, and if it stops being 0, then we break. And if we failed, so if this remains 0, we want to just add address plus equals, let's add a page 0x1923, so 4 kilobyte standard page size, and then we try again. So we write trampoline box is equals, now we need to cast this again to the right type, virtual alloc. Okay, and now we specify where we want to allocate the memory, and if it's possible, then it will succeed, and if it's not possible because this memory is already used by something, then it will fail with null, and then we just go to the next page and try again. So you size, we want to allocate our defined size here. Then the allocation type, mem commit mem reserve, comma, and of course we want to be able to write its own page and execute read write. So we could later, for better security, switch this to just page execute read without the write option. So what we get now is some memory close to where we want to modify our code. So we use our nice manual coding mechanism to write new code. And what we'll be doing basically, so we know we need 12 characters, so we have 8 here, we have 3 here, sorry, we have 4 here, 3 here, so that's 7, that's not enough. 8, 9, 10, 11, 12, that is enough, and then we have 2 characters that kind of are left behind, so we know we need to replicate this part of the code, and then we can jump to the next address here of the original function. So let's do that quickly. So asterisk code punct double word p double word plus plus equals 0x. Now we need to revert the byte order. That's of course always a bit annoying. zack, zack. And first we will do it in a very naive way. We'll just copy the code and then we'll try it, and I guess we'll see that it will not work, and then I will explain why. So the next one is 3 characters. 3 characters is of course not so great because we kind of don't have a 3 character type, but we can use a word and a byte to get 3 characters. 0x, oops, 0x. So we take this character and this character, oops, and this goes here. So semicolon is equal 0x. That should be correct. And then of course the long one, which is, how much is it? 7 characters. So that is kind of also a little bit annoying. So basically it's just another times this thing here. Zack, 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 so until here, zack, zack, and zack. Okay, so this match to this. And now what we want is we want to jump to our to the original function. So we take we can for example copy this code here already. Now we should also label what we have done. So this is this, that is that, and this is this. Right, we just need the right address. And to jump to the right address we want to basically jump here, but we kind of don't want to have this hard coded. So let's open the calculator. So that already is good enough. Switch it to hex. So this would be the next address. We want to subtract that from it. So it's e in decimal is 14, which is kind of correct. So what we could do is here is we take this plus 13. So this should bring us, it should jump us to where we want to jump. Okay. Let's put a breakpoint here. And I said we could set a protection which is a bit safer on our code. Let's do that. So here we have our code. Then we need of course to let's move this alt protect somewhere at the beginning. Yeah, let's put it there. So we go with trampoline. Size stays the same, and then we just want to execute read without write. And we don't care for the old value, but we need to provide something to save it, and we should maybe add a comment here. And here, let's write this out what we do. Okay. So let's run it. And okay, we are here in our detour function. And then we load our trampoline address, then we jump here. We see here it looks kind of quite right. Let's quickly go here. Let's see if this actually works. So it gives us to here. So this is correct. The rest on the top is not disassembled correctly, but we see that it would jump us to the right offset. So let's step by step. And here, as you see, bam, we crash. So what happened? Well, we copied here this instruction which takes a relative address, and this ended up, of course, not longer be true. So um, it did not contain the right memory address anymore, since the location of the code changed. The relative offset was the same, but it didn't point where it should point anymore. So we can see here in the disassembler here, basically this function, when it's displayed in a more friendly way, then Microsoft does it, is a compare at the memory position current instruction pointer plus this with the register R11D. And of course our IP, so our instruction pointer now is something completely different. We are here instead of being well, a bit somewhere there, and then thus of course the whole memory address here is not valid. So let's quickly copy this code here, put it there so that we see a bit better what is happening. And what we need to do is we need to fix this somehow, and a way to fix this will be to dissect this opcode more thoroughly and adjust this value here. And this was the reason why we wanted our detour code to be memory-wise close to our DLL, so such that here we don't need to translate a long opcode into one that only makes a 2 GB offset. So let's analyze it. So we have this 7, 2, CD and 6. So let's see, 0, 0, that sounds good. 7, 2D, T6. So here those 4 characters are our offset, and the opcode itself is actually 44 39 1D. So let's re-engineer our code. Oops, correctly. So that will be 39 34 1D here, and a double word which contains the offset, and the offset was 0x, and here we can copy it from here, 1 2 3 4 5 6 7 8, just add the missing zeros, and let's make everything uppercase for consistency. So at this point we still have the broken code. We have just written the opcode down in a more correct way. So what we need to do next is to change this address. So what we will do is we'll calculate the displacement, which is representative of how far our own code is from the original detour code. So 64 this trampoline displacement, or let's just call it displacement. Displacement is equals 64. We go with our trampoline message box, and we subtract from this the original message box's position, and this might be a positive or a negative number, although in principle here, since we are only going to plus direction, we know that it will be positive. Other strategies would be to allow to search in both directions, and then we might get a positive or negative value, but here for simplicity we know the direction, so we know this will be positive. And here thus we just subtract our displacement from the preset value, and while the opcodes until here across Windows versions will usually remain unchanged unless it's like really a big update, this displacement here, or rather this offset here, you can more or less expect it with every new revision of the user32 DLL that this might change. So this emphasizes the necessity of a automated mechanism and not just manual operations. So if we, for example, would always know that this is the structure, we could then just read the value from original value here from the backup, and then calculate our displacement relative to it. But then, of course, we still assume that there are no other changes to the function. More automated approaches, what they will do is they will, in fact, analyze the opcodes, copy them, and then for every opcode they know that which can have a relative offset, they will do an automated adaptation of the displacement. So basically what we are doing here by hand, the libraries will do this automatically. Right, so we have the right displacement. This is our jump code, so this should be all fine. Then it might already work. Let's align here the comments, and let's run it. So zack. So again, we step through our function call. Now it didn't crash, and now we load the address and we jump to the rest of the function, and voila, hacked message box, fail now, no, then the thing repeats because we have another message box, hacked message box, success. So at this point we can already modify the behavior of this function repeatedly. Now we also see that each text is logged, so actually we should add here a new line so that we get a new line for every single entry. And now, of course, we could also change the logic of the function to make it do something automated, for example. For example, we don't want to ask always the user whether the application should crash or not. So let's see if VCS CMP, so white string compare text, comma L. Let's copy the original text. Fail now. Fail now. And if this is 0, so if this is equals, then we just return ID no, and we just don't do anything. I mean, we could still print the content, so maybe let's leave the print function, but we will not be showing the message. So now when we run the application, the only thing that will happen is that we will only get the success message box shown, and that will be that. So zack, success, and the other message box was suppressed. And of course this can be done with arbitrarily complex functions. So another use case where such a mechanism might be interesting is if you have some sort of library that let's say it prompts you to enter a COM port number, and it's a very old library. It only supports like a handful of COM port numbers, but you have like a 2000 USB COM ports, and it doesn't offer you the right value. You could, for example, override a function that opens COM ports to ignore whatever you have entered, and then instead use some COM port value that you have specified, which does exactly what you want. Okay, so this much to this. Now, of course, the question would be how this knowledge can be applied outside of our own application. So here, for now, we just had our own program, which was doing whatever we wanted it to do. So we have a lot of control. And while, as I give the example, some device library for some very old hardware might be a use case where you might want to and could so simply override functions. A more common use case would be that you would have some control application, just a library but a full application, and there you would have the same necessity that you need to change some parameters for it to operate correctly on your system. This can be arbitrarily complex, so it might be a situation where you know that the application always crashes because of something. For example, a lot of computer games, very old ones, might not take it nicely to be run on a computer with more than 32 cores, and they will bug out. So in such situations, manipulating information returned by the operating system, like for example the CPU count, would help to easily resolve such a problem. Any questions? Okay, if there are no questions, then let's continue with our example. So we will want now to create a demo application in a new project, which we will manipulate externally. So something that is a little bit more complicated. We again start with a new project. Let's call it process hacking. Create. And we will need now, of course, a bit more than just one project, since first we need some target project to mess with. So just copy our initial very simple demo code. So this thing just asks us if we want to fail and then fails or not. But what we actually want is we need to add two more projects. One will be a loader application, so something that some application that will start, prepare everything, then start the other application and do the modifications. So let's call it my loader, and then we'll also need in depending on what we are doing, such a loader might already be all we want, because if the modifications are sufficiently simple, then we could in principle write the whole code inside. So here we have a C function that does things which can do reasonably complex things, but if we would know that we need only a very limited, very minimal modification in the original function's behavior, we could basically just write the whole code into the application directly without any additional steps. But this, of course, is somewhat challenging because it requires us to write nice position independent assembler code, and it might have a much higher complexity. So here this is still a very simple case, but if we would want to be more complicated, then this of course will mean to write a lot of very basic code by hand. There are ways how this can be simplified. So you can use Windows to generate, for example, a DLL which contains only position independent code. Then you extract this code and then you can inject it into another process. But that is already quite a lot of steps, and it still requires us to create a DLL. So the simplest way here that can be done is that we actually create an own DLL, which will contain most of this demo code here, which we then inject into a process, and the DLL will then modify it. And the nice thing is that, except for the hooks themselves, we really don't need to write any particularly difficult assembler code. You can just write C functions, and that's that. And as I mentioned before, there being already existing hooking libraries, we can just use those, so then we don't even need to write any assembler code at all. But since this is a lecture showing the low level aspects, so we want to do all this stuff manually. If we have enough time, then I may show you one of the nice libraries that you could use that would do such things on its own manual without you having to manually create those hooks. But for now, let's just go with doing everything by hand. So as I said, we need also yet another project, the DLL. What was that new? Add new item. I need to click here. Add a new project, and we want a DLL. We already used one before, so, and let's call it our hook DLL. I think I didn't mention it, but the process of intercepting code execution with some own code is usually called function hooking. So why it's called historically like this, I don't know, but it sounds like that you are installing some yeah, hooking somewhere in, and if something happens there, then you get a notification, so something will then pull on your code, so to say. Well, so we have here our DLL, but before we do something with DLL, first, of course, we need to somehow create our project. Let's set the loader as our startup project, so that if we press play, it will be built first. And then, of course, we should also set our project dependencies, that our loader will depend on our target process and on our hook DLL, so that if we modify one of them, although in principle, let's just maybe only make it dependent on the hook DLL, since the process itself here, we don't need to modify that anymore. So usually the whole point is that your target process is not modifiable, not easily. You don't have the source code to do so. So it's some sort of, as I wrote the example, some old control application for some something that you can talk to through the comport, and many such old programs, they had like comps 1 through 8 or 1 through 9. Back then no one have thought that you could have a computer with 24 or even more comports, so they offered a drop-down selection instead of a line edit, and that was convenient at the time, but nowadays might be a problem. Of course, a simpler solution would be to just change the port numbers on Windows, so that for those devices that only support lower port numbers, you just have them on the lower numbers. But then, of course, this still would limit you to the amount of such devices you can have. So an approach where you can actually override the port selection is a very legit application of the things that we are learning here. So we won't be modifying this anymore. We will be only modifying our loader. So we will, of course, now need to somehow create a process. To load the code into, and we will of course need to create the process itself. So there is a function on Windows called create process that allows us to start other processes, and nicely enough, this function has a few flags, and one of them allows us to create the process in a suspended state, meaning the process is created, the code is loaded, but the code has not started executing yet, thus giving us the opportunity to manipulate it however we would like. Tools, so let's use it. So first things first, we of course need to know where the application is and start it. So since the way this is set up, if we go here and rebuild solution, we will see that all the applications end up in the same folder, including our DLL. We have our loader, we have our target process, we have our DLL. So we could, for example, get just the path of ourselves, and then only swap out the name of the file itself. So chart my path small t chart my path. Windows has a nice macro, max path, which is 260. That's the, it's like if you include Windows, that's like a typical path length limit on Windows, although it is more limited to the standard Win32 functions. The Windows NT kernel as such internally can handle paths up to 32,000 characters, so substantially more, and you can, using the right prefix, enable this long path usage, or you can just use the NTDLL functions directly instead of going through the wrapper functions in kernel base, kernel 32, etc., etc. But usually, for example, Windows Explorer itself doesn't handle long path names nicely, so generally on Windows you should just try to keep your paths lengths below 260 characters, and thus, of course, it's also quite a convenient size to create fixed length path variables without using STL strings or some manual memory management. Here we just define something, and we can usually assume that it will be long enough. So to get the, so now we will use another function to get the path of our own application. So whenever from wherever a process is started, when you call this function, it will give you the correct path. It's get module file name w. So as the name suggests, it does not only work for our own application, but if we would have a handle to a DLL, we could also get those DLL's path. But if we pass null as the module handle, it will apply to our own process. Path, sorry, my path, comma, and the function wants the maximal length. So of course, if we would be doing some production code, we would now check whether it was successful or failed. It might, for example, fail if we don't have enough room in our path variable, but you know, this is quite short, this will work fine, so we skip this, and now we want to get rid of the last part of the path, because this gives us the full path with the file name. We want to get rid of the file name, so we can use the vcsrchr. So it's white char search reverse character function. It basically searches the last occurrence of a character in a white string. So we go for l \\, and now again we should test whether it works, whether it found something, or because if it doesn't find, it will return null, and null is of course invalid. But since we kind of assume success, we just add +1, then we dereference the whole thing, and we set this to 0. So we basically just add a terminating 0 where the last \/ was, and we assume everything works. So it's not a safe way of doing things, but it's a working way. And then we create two more variables. One will be exe. For the exe we want to start, and one will be DLL. For the DLL we want to log into that exe. So VCS CPUI. We should use the save version. Destination is this, comma. That's the maximal length that's allowed to be copied, and here we now take our truncated myPath, and then we use VCS cat s. That's for string concatenation. It allows us to append a white string to an existing string, and that was for sucking eggs, and then we just repeat the whole thing for our DLL, and the name of our DLL was hook DLL. DLL. Yeah. So we have the two paths, and then we can proceed by creating a process. So create process W. So exe path, oops, comma, command line null, attributes null, security null, false. Now we can specify the flag to make the process started in a suspended state. Create suspended. Environment null. Current directory null. When you provide nulls there, it will just take the defaults. And now we need two structures: the startup infrastructure and the process infrastructure, which will return, which will receive the resulting results. Info v se and information pay 0 reference se reference pay. Why is it not happy? Exit path. Oh, call this my exit. That's not quite right. Let's call it then my exit. Right. So this will create the process. It could also, of course, return 0 on a failure. And for now, we won't be doing anything but just resuming it. So, so the way this process is created, it will get it will be created with one suspended thread, and this thread needs to be resumed. And then, of course, since we got a few handles here, as you might remember, we also always need to close them to not have any resource leaks. So the thread handle itself and the process handle. Okay, so now it will just start the process. It will not do any modifications. So as we see, the process just starts normally. What we also can do now before we resume is we can create the process. So now it already exists, and we can attach our debugger to it. Attach to process hacking, attach. Then we can go here and put a breakpoint somewhere, for example here, and then we can run the code. We get a breakpoint that allows us to set a few more breakpoints if we want, but we ignore that. Then we get, of course, our question, and we didn't run into the breakpoint because I chose the wrong option. Let's repeat that. Debug, attach to process, attach, resume, breakpoint. No, I don't want to fail. Success. And then we get into our breakpoint into the other process. So, as you also see here, by the way, Visual Studio allows us to debug multiple processes at the same time, which is quite convenient. Okay, so now what we need to do is we need to somehow load the DLL into our target process. So let's do that. Let's create a function for that, which will be doing it. And the simplest method on Windows how this can be done is by using the create remote thread function. We will want to pass to it the process infrastructure by reference, or I mean, as a pointer, and then we will also want to pass to it the DLL path. So const. Okay. So first. So the way we will be doing it, we will first need to know how long the path is so that we can allocate some new memory in our target process. Then we will copy the path, the DLL path, into our target process, and then we will use this create remote thread function to continue. So to add 1 for the terminating null, and then times caesar of let's go t, since we have here white characters. So void address is equals virtual alloc, but we take this time the X version, the extended version, which takes a process handle. The normal virtual alloc just worked on the current process, and then we can specify where we want it. In this case, we don't care. lp void address. So we have null, then size. Size we have here, or let's call it usize to be consistent with our other naming convention. Mem commit und pagen read write. We want to be able to read and write. It doesn't need to be executable. And now we write process memory handle address. As you might remember, every process has its own memory space. So so this address which we obtained here is not valid in our own memory space. So we need to use a special function that will do the writing for us, and by its written, we don't care for the written value, so we pass null. And this write process memory then does this on the kernel level. It looks up the provided process's memory allocation and then writes to the right address inside the process's address space. There is also, of course, a complementary read process memory function. Okay, and now what we need is we want to use this create remote thread function. So handle we have a handle on the thread, create remote thread that takes again a process handle, so that as the name suggests, then some attributes null, stack size 0, it can be default, and startup routine. And that's a bit problematic because here we need to have a function address which already exists inside the other process that can be jumped to. We could of course use this write process memory to write a whole function inside the target process's memory, but that would be significantly more complicated. So for now we want to do it a simple way. So we need some function which would do exactly what we want, which we can expect to already be able to find in that process, and there is one. It's load library W. As you might remember, it loads the library, and the first argument it takes, and the only argument it takes, is the address. Not the address, the path, the address to the path, which library to load. So this is super convenient. We can just take our own address. The things would be much more complicated if we would be working here across bitness boundaries. So if we would have, for example, a 32-bit process into which we want to inject from a 64-bit process, or vice versa. But here, since we are all working in 64-bit, we know that the address of load library W in our process will be the same as the address in the other process. So the way Windows works with regard to selecting addresses, base addresses where DLLs are loaded, is that it will for all processes on the system load the same library always to the same address. The reason for this is that this way, as the name suggests, the dynamically loaded library, also sometimes called the shared library, Windows can share the memory pages across multiple processes. So if you have like 10 processes and each of them wants to have a copy of user 32, or in this case kernel 32 DLL, if for every process you would load the same library into memory again and again and again and again, that would be of course incredibly wasteful. So what Windows does is it loads the first time it loads the library to some address, and then for every subsequent load of the library it will just pick the same address. And the way things work here is such that the code might be position independent, but it also might be position dependent. So you couldn't map the same DLL into different processes at different offsets. If the whole code of the DLL would be always position independent, that could work. So then you could have multiple processes sharing the same DLL, but seeing it at different places. However, Windows has to also handle the situation where you have a lot of position dependent code, which means it would, each time it loads such a DLL into memory, even though it might select a new address while it loads it the first time, it would then go through the DLL using some built-in mechanisms and tables with hints where position dependent code resides, and apply such displacement calculations as we have done. So the DLL would be defined with some default base address, and all the position dependent code as is written on disk would be relative to this address. And since Windows, however, will nowadays load a DLL not to the address the DLL wants to be, but to some randomly generated address at start, such that across different systems you cannot predict a load library W's address, for example. So here we can retrieve an address, but each time we reboot we would get a new one. This is called address space layout randomization, and it is a quite important security mechanism. So since the addresses now are no longer what the DLL expects, also this mechanism was introduced long before ASLR, because you might have two DLLs which two people that doesn't know about each other selected the same base address for. So even Windows 98, 95 needed to be able to handle the situation where it cannot load the DLL to where the DLL wants to be loaded. It needs to give it a new address. So for this, these mechanisms have been initially developed, and what happens in such a case is that the image loader of Windows then loads a list of all the position dependent offsets inside the DLL from the DLL. So this list is created by the compiler, so such that it doesn't need to disassemble everything and go for everything. That it knows where to apply the fixes, and then there it will take the values which are there, and then add or subtract to them the right displacement offset such that they will be correct. So given this, Well, one could, as I mentioned, try to share a DLL across multiple processes. Every code page which has position-dependent code would need to be rewritten, and then still a new page would need to be allocated. So this would be impractical, it would be too wasteful. Thus, on modern systems, there is a bit trade-off between security and performance, or rather security and memory usage, such that while any DLL will be loaded into a random address at start, once it's loaded, it will remain at this location even across processes. This is why here we can so easily retrieve this location. If we would be working across boundaries of 64 and 32-bit code, there are two copies of NTDLL, two copies of user32DLL, one 32-bit, one 64-bit. So if we would do this, we would get the address for our bitness, but not the address for the other one. And there are mechanisms how we could load the created processes memory layout, find there the loaded image, and then in it find the right offset. But this, as you can imagine, is quite complicated. So for now, here we will just use this simple mechanism, relying on the address being always the same. Okay, let's continue. Well, in parameters. So parameters or parameter. So this thing, let's see here, needs to be of this type, this LP startup routine, which takes one argument, and this is a pointer. It's a pointer of a not closer specified type, but we can just feed it there our memory address. And given that library also just takes one pointer, the type of the pointer, as you might remember from our lectures about function and calling conventions, the type of the pointer doesn't matter. It is just an address. The type matters only for the compiler to throw errors and warnings if we are doing something that we shouldn't. But here, providing the address of the string will be perfectly fine. It's exactly what the function on a code level expects. And yeah, and the last flags, of course, here we can also create the thread in a suspended state if we want, but we don't really need to. So actually, let's just let it run from the get-go. And thread ID, we are not interested in the thread ID, so we can just pass null, so we don't get this value back. Here we should add some error handling just to be on the safe side. If this is invalid handle value, then we bug out. This means something failed, and else it's fine. So if it's fine, then we could wait for the thread to finish. Wait for single object, zack, forever. And then of course we need to close the handle so that we don't have a resource leak. Okay, so, and after this thing ran and finished, we can resume the original thread of the process. So let's run it. Something didn't work out quite right. Let's see what happened. Oh, we didn't call our function, obviously. Then it couldn't have worked. Right, so we want reference PI and wait. Yeah, DLL path. Okay, let's close this running. Since we are now starting and stopping processes, we should have a task manager. We have the normal Windows task manager. We should install a better task manager. Like Task Explorer. It's an open source task manager from GitHub. Ausführen, installieren, English. And let's start it. This we don't need. And let's sort them by time. Okay, so we don't have any. This we also don't need. So Yeah, that looks useful. Right, so let's try again. Still didn't work, so let's see what we didn't forget to call the function. So let's see where we are failing. Oh no, sorry, of course it didn't work. We have not made the DLL do anything. So this loads the DLL, but the DLL is not doing anything because the DLL is not yet has not yet done anything. So let's see. So we select the program here, and then we can here go to modules, and we can look for our hook DLL. And voila, as you see, it has been loaded. It just didn't do anything because it doesn't have any content in its main function. So now, of course, we need to edit some functionality so that it does something. As you can also see, this task manager is quite powerful. It allows us to see a lot of information about the processes which we are working with. Okay, so let's go to our DLL. Here, DLL main, and let's from this function here just copy most of it. Windows should already be included in the DLL, but the printf isn't, but we don't need the printf anyways. Don't like this additional indentations that it always does with extend C. I mean, if we only have one function as we do, we could just do it like this, then we don't get the inconsistent indentation. That's nice. Okay, so to here, zack. This we won't need anymore. And we want process attach. So process attach is when the DLL gets loaded, as you might remember. The other ones we don't care for. And in principle, we could uninstall the hook if the DLL gets unloaded before it's unloaded, because otherwise, of course, then the trampoline and the detour code will still be in place. And if someone tries to call MessageBox Fair after unloading our DLL, it would lead to a crash. But as I said earlier, installing hooks or uninstalling them after the process had already started operating is, of course, somewhat dangerous. So usually if you have such injections DLLs, you just say, well, they will never be unloaded. They will just, when the program terminates, then they will be unloaded together with everything else. Actually, we should make a function for it. Let's call it install hooks. I mean, we might have more than one. Void hooks. Zack. Okay. Good. Let's run it. And you see, hacked message box success. The behavior of the program has successfully been altered. And of course, there are more than one way to achieve our goal. But first, are there any questions? Okay, no questions, so let's continue. So generally, this create remote thread is a very common mechanism to inject code into processes. Together with the load library function, it's really convenient. But of course, one might either want to use some other mechanism, or I mean, for what reason? That's a good question. Maybe for avoidance. So you can easily detect such a create remote process from a driver, and for example block it system wide. Although that would break a lot of Windows functionality, so you would need to be careful which programs you allow such things to do and which not. So if you want to bypass such create a remote process restrictions, you could use another mechanism which does not offer a callback in the kernel, so that it cannot easily be blocked. That will be asynchronous procedure calls. So let's see how this works. So we will for this just create another function and use the other method to achieve the same goal. Although maybe before we do this, let's inspect in a bit more detail how everything works here. So we have our DLL. Let's put a breakpoint here. Let's put a breakpoint here. Let's run it. But though that's already too late. We should create our DLL also suspended, and then resume it. Resume thread. Oops. And we should put a breakpoint here. Okay. So at this point we have set up everything. Debug. We can attach to the process. Oh, apparently we left a few unterminated process from earlier attempts. Let's just kill them. Okay, this one is the latest one, since as you remember here they are sorted by creation date. So we attach, and we can also inspect them a bit more. So threads. You see here there are two threads created on this process. One is in bold. That's the main thread that was created during process creation, and we'll yes, and we can see where it is currently being held. This address will be an address in our function. It does not load the symbols for it, and other than that we just see some Windows kernel internals which we don't care for. And our other thread, okay, this is annoying, it doesn't load our own programs symbols, only the Windows ones. I think I'll just restart it. I think there is a small bug when saying yes the first time to whether I should download symbols, and then it does not update everything. This we don't need for now. Start time is still active. Process hacking. Let's see. No, it still didn't load the symbols. It says symbol loading. It might need some time to actually download all the symbols. We can also see here some network activity, so we could give it some more time. Like our Visual Studio also needs to download all the symbols, and since it's doing this in series, it probably just didn't came to loading the ones we want to see here. Okay, I mean, if it doesn't work, we can also observe the things here from our Visual Studio. That will be also convenient. For now, the thing is okay. The thing is busy. Let's just leave it be for now. So but as you see, we have these two threads. So here we can attach the debug, attach to process. I would already attach to it probably. Then back window threads. Let's see. Yeah, we already attached. So here we see the more or less same thing we have here, but it doesn't show the process name. We have 3 threads. That will be our loader. We can also see here where it is. So yeah, and here we have our other 2 threads, and you see here they are both hanging in NTDLL. This is where all the threads start their existence before the control is passed over. Yeah, this thing just didn't. It is still busy with symbols. It just needs at some point to download the NTDLL symbols before it will show something useful. So all the threads always start their life there. We have. Okay, we don't have the breakpoint. That didn't set. Right, we don't have this breakpoint because it is not loaded yet. But if we have set it, the debugger should correctly activate the breakpoint once the DLL is loaded. So let's press on continue. Let's see. So this will continue over this, and this will then break here. Let's continue. So here we have again this built-in breakpoint, and voila, we are now in the breakpoint inside our DLL. So when we see here the main thread is still hanging in this start situation. Our own injected thread is now at a hook DLL main, and then you can see here there are like three threads which just appeared out of nothing. These threads are used to load DLLs in parallel, which speeds up process start. They are created by NTDLL internally before any of the other threads is actually resumed. And after some time they will auto-terminate, so we don't need to care for them. We can also see in the call stack that here our own DLL started in the call stack its existence at this user thread start in NTDLL, like we see will be the case for our main process. So here we continue, and then that thread has terminated, and here we waited for it to really terminate, and then here once we resume this we will end up in our process. So there we can just suspend it, and then we see here so that the main thread is in this message box mechanism, and then of course here it started its life again at user's thread start in the NTDLL. So this much to this. Now let's try the other mechanism which I hinted at that we could use in a more sneaky way to inject some DLL into a process. So we will be using the user asynchronous procedure call mechanism for that. So APC can comment out this method and use our user APC method, and at this place it will be kind of the same. So we still need to allocate some memory, and we need some address to jump to, but the way we trigger this will be different. So okay, measure Q, use an IPC, and this takes again we need the right type, but effectively we just pass our library function, comma, thread pi. So in Windows you can queue a asynchronous procedure call to a thread. You just need the thread's handle, and then what it will do is it will call this once on Windows the process runs and does some own code, and whenever it needs something from the operating system it makes a transition into the kernel. So it calls a special function which triggers a transition to kernel execution. Then the kernel is doing some own things, and then once it's done it returns back a control to the user side of the process. And in some cases, not on every, but in some cases when transiting back from the kernel to the user process, you can have scheduled things that will be executed before the control actually returns to the thread that transitioned earlier into the kernel. And this asynchronous procedure call exploits this, so that we will be able to make the main thread of our application do something before it will actually start the main function of our own application. Okay, so we have here this, and then of course we need an argument. Those of type long ptr, and it will be just the address of our memory, and we want to return success or false. Okay, so in this case we only need this breakpoint, so let's run it. Then let's attach it, debug, attach to process. We have the other one not yet terminated. Attach threads. So here you see we only have one thread, not two. And now when we continue, we get this default breakpoint and then the breakpoint in our DLL. And here we are sitting now in our target process. The other already terminated, so we can see here my load already is gone, just the process hacking. And now we have in this DLL load event inside our main thread. So let's go to the call stack, and as you see here, so we start always more or less at the same place, and then at some point before we will invoke okay, let's load this one. Before we will invoke the main function of our application, our load library. So we have here this dispatch asynchronous procedure calls, and it was triggered from anti-test alert, and that then took the address and jumped to it, providing it the argument which we have set up for it. And then of course from here the normal DLL loading routine takes over. And once we are done with this, then again we have already all our hooks installed long before this thing here entered the main function. Any questions? Okay, no questions, then let's continue. So of course the next approach would be to do something even more complicated, like override a portion of the application. So this asynchronous procedure call is quite a good and reliable method. It's not as easy to block as this create remote thread approach, and it's much more difficult to detect, since as said there are no hooks in the kernel that would allow you to monitor those things easily. But we of course might want yet another mechanism to inject code into some process. So let's do that as well. Again, we copy a little bit text, zack, and let's call it shell code. So we comment this out. So the approach here will be to change what the main thread actually wants to do and redirect it to our own let's rename it and redirect it to our own code, and only once we are done then return control to the process. So this can be done on Windows quite easily. We first need to get the threads context ctx ctx context flags equals context control bar okay equals get thread context. We need to pass the handle p thread comma then our context. We write into this flag field to which part of the context we want. So the context is quite large, but we are not interested in most of the possibly available informations. We just want some of it. And of course we will add here some for checks, false, lowercase. And on context we now have, let's inspect context first. We have a huge amount of registers and flags and stuff. So we have some segment registers, we have some debug registers, then all the normal registers you should already be familiar with. The program counter, so the one that tells the whole mechanism where to start execution. Then we have some more registers for the floating point arithmetics, which we are not interested in. Some more vector registers for AVX operations, and then even more potentially interesting things. But what we are only interested is this instruction pointer, which we would want to set to some new value pointing to some code which we yet first need to write into the process's memory. And then of course once we have written those things, we just need to update the context with set thread context, and then we have the same check, and then if everything was fine, return true. So what we do need, so what do we need now is a function which will generate some code inside of the um, target process, which we will then instruct the thing to jump to. The problem here is that if we would set RIP to just the DLL, that this would not yet, to this load library, this would not yet work quite well. What we could try would be some very hacky approach where we modify the register which should hold the first argument to jump to, but that might later down the line break other things. So we should go here with a more elegant approach, which will mean that we will create some shellcode and then properly save and restore all the register values such that we do not break anything. So void asterisk write shellcode. This thing will take a process handler. Process. It should take the original return address. The 64 so where it needs to return control to once it's done doing its thing, and of course we want the DLL path for the DLL to be loaded. Okay, so shellcode, write shellcode pi process, comma, the original value of this and our DLL path. Zack. Okay. So let's create a few useful things. So our union thingy from before, which is helpful to write code manually, will be very useful. Then we will need to some buffer to write code to. Nutra my code. Let's give it a page. It initialize everything with zeros. Code.pb equals my code. Okay, and let's start. So for easy debugging, what we could start with adding a breakpoint. So something that will trigger the debugger. So asterisk code dot pb plus plus is equals 0 xcc. That is the int3 interrupt. We might, of course, not want this in production because this will cause a crash if we don't have a debugger attached. So instead we will want to keep all the offsets, have here a no operation, nop, which basically is an opcode which tells the CPU to not do anything. So it just takes some place and doesn't do anything. So it's quite nice, and we should of course keep track of our offsets. So we start at 0. Then of course we are done. The next offset we can, I forgot the semicolons. Next offset we can do something will be offset 1. And before doing too much, we could already test whether this works. We will just need to write it to the process. So of course there will be much more code needed, but just for now let's start with that. We will want some length of the total shellcode. So let's make size size is equals size is equals, and what we can do is we can copy those two. Since we always incremented, the total size will be current size, which is bigger minus where we started. Okay. So void asterisk and let's copy this from here. Virtual alloc x size page read write execute. Actually, it does need to be write read and what was it? Execute read. What is it? Execute read. So we have our virtual address. Then we can write was the I just copied from here. Yeah, right process memory. Yeah, we only have the handle, so that's changed. Process address, okay, right process memory, and we return the address of our shellcode for it to be jumped. So I said this will trigger the breakpoint and then crash the application, but just to see the basics, this is a good enough beginner. Yeah, so before we resume, we need to attach and go back somewhere. Here. To cast it to the right type. Okay, debug, attach to process, attach. So continue. So this is the built-in breakpoint, and we continue again, and bam, we have our breakpoint written in. Oh wait, did that crash? That's not our breakpoint. That's just a crash, but it's probably where we allocated. So let's see what we have done wrong here. So we have our code. We have the breakpoint that should be right. Plus we have also. Let's put a breakpoint here. Better even let's put a breakpoint there. And first let's see. Byte process memory. Oh, of course we wrote that's a big mistake. We were supposed to write our code and not the DLL path into the memory there. Now it will be fine. Debug, attach to process. And we have the other one, the broken one, still hanging around. Let's kill it. Zack, attach. Continue. So we have the default breakpoint. And now here, voila, we have our own breakpoint. Zack. So, as you see, we can just write code into another process and it will be executed. But I see we are kind of already running out of time. So for today, let's just finish this up in a rather very basic way. Let's just add the jump back to the original address, and that's it. So here there will be a to-do for the next time. And for now we will just what we want to do is we want to jump to can do a long jump jump to our return address. We had that here. Chuck. So move rux code return address and then jump rux. And that should work correctly. Yeah. Let's try it. So we are here, then debug add attach to process, attach, continue. So that's the debugger breakpoint. This is now our breakpoint. So let's step through it. And now we are in the thread start function. When we continue from here, we get the normal messages. As I said, we still need to implement a code here to actually load our library, but since we only have a few more minutes left, we will do that next time. And at this opportunity, then we can also write a much more sophisticated shellcode that will do a few more operations. So we can, for example, load the library, but not rely on its DLL main but behavior, but instead have a dedicated function to install the hooks and so on and so on. So that will be fun. I will upload the current code to Moodle. Only of the I can upload both, I guess. And that's that. If you have any questions, you can ask them already. The next lecture will be the last lecture, so if you have any questions with regard to your final project, that would be the best opportunity to be there and ask those questions. And that's that. So let's stop recording.